Okay, so before we begin, a couple of pointers. We found while grading the midsem, we found that some people were were communicating during the exam. I mean that's of course an unfair practice, and again goes against the code of conduct that you have agreed to. So we have penalized appropriately, and I ask all of you to let me know if you know of any other cases of cheating. I mean, of course, uh, in this online mode, it's much easier to cheat, and we can only put so many checks and balances. But I know most of you have done the exam taken the exam honestly. So certainly those who are resorting to unfair practices are, because of the way the grading scheme works, which is relative grading, is going to affect the honest ones in the eventual grading scheme. So please do let me know. And as I said before, you don't have to tell me who you are. You can create an anonymous Google account and just send me an email, and we can verify your claim. Uh, there are ways that we know how to do that. So yeah, so please do let me know if people are resorting to unfair practices. Okay. Also, some of you have been emailing me. Actually, a lot of you have been emailing me about increasing 1 mark here, 1 mark there. I mean, this for the most part, I'm not going to respond if the claim is not justified. I simply don't have the time to respond to individual comments asking for clarification. Please ask your TAs, and I mean, if in exceptional cases I can take it, but for the most part I will not be able to take it. It's simply not. I simply don't have so many hours in the day, unfortunately. Okay, so let's now talk statistics. I hope you can see my screen. I have now updated my Teams application, and I hope it's working. So if there's any problem, please.
Sir?
Yes?
Did you get any information about in which days the holiday associated with the 19th one?
Not yet, but we will all get an email about it. I mean, it will be a campus bulletin email, and we will all get it, and I will act accordingly.
Okay.
I think it's a bit too early, but they usually tell us the week of the, maybe few days before, based on whatever circular the government announces. We are usually governed by central government rules, but for some things we are state. So it's a bit unpredictable. Yeah. Okay. So you remember we were talking about maximum likelihood estimation, and so we have the samples x1 up to xn, and from some distribution with some unknown parameters theta, and we, by definition, this random sample are independent random variables, and so the likelihood function is the joint PMF or PDF, as the case may be, and which will be of product form. And we are going. This is the likelihood function, and to estimate our parameters, we are going to try to maximize this. And I gave you one example in the Bernoulli case, where it turned out that the maximum likelihood estimator for P, the the P in the Bernoulli P random variable turns out to be the sample mean. And I gave an application of this. So now for the first half of the class, I want to go through some other examples to show you what happens. So, so what was my convention? So this was example 1. So let's do example 2. Okay, so again I will say n independent, let's say Poisson lambda trials, x1 up to xn, and find the maximum likelihood estimate for lambda. There's only one parameter here again. So what is the likelihood function? So the first thing, as usual, you want to do is to construct the likelihood function. Because the Poisson is a discrete distribution, this is a PMF. And you all know and by independence, you just need to take the product of the individual PMFs. So the PMF for the Poisson lambda is e to the minus lambda. Lambda for the first one is lambda to the x1 by x1 factorial, etc. Same thing for everybody. So e to the minus lambda, lambda to the xn by xn factorial. And now you can see you have you have n e to the minus lambdas. So e to the minus n lambda times you have lambda raised to x1, lambda raised to x2, etc. Product of those. So it's just lambda raised to x1 plus up to xn. And the denominator you have x1 factorial up to xn. Okay. So you want to maximize lambda. Again, lambda is in the exponent and all that, so it's better to take the log, as I have said before. So log f of x1 to xn given lambda is minus n lambda for the first term plus x1 plus up to xn log lambda minus log of whatever x1 factorial up to xn factorial. But the important thing for us is this is just some constant. This is independent of lambda. We are going to maximize this value with respect to lambda, right? So we are going to take the derivative with respect to lambda, and this guy is clearly independent of lambda, so I don't care for what it is, right? So d by d lambda of log f, I just write log f for short, is minus n plus x1 plus up to xn divided by lambda, and which we will set to 0. So the value lambda hat at which this is 0 is clearly lambda hat equal to x1 plus up to xn by n. Again the sample mean. So just like the Bernoulli case, this is also the sample mean. So the best estimator for lambda turns out to be the sample mean. Okay. I should note that I am not verifying that this is the maximum. I mean, I'm just so maybe I should clarify that I am not checking that this is the value at which log f is maximized, but this is something that I encourage all of you to check. So use either the first derivative test, second derivative test, whatever you like, whatever you are comfortable with, and you verify that this is at this value of lambda, this log f will be maximized, which means f will be maximized. Okay. So what is an application of this? So I won't do a full example, but I'll just give you an application. suppose you are given the number of traffic accidents per day. In a city. Okay. So you know that the probability for any single accident is low, but you know that there are a large number of drivers. Right? So this is like the Bernoulli NP, where n is large and p is small, and so that is well approximated by Poisson. So I mean, this is a typical so number of drivers large and probability of accident small. So it's natural to be naturally approximated by Poisson distribution. And what's the parameter for Poisson? So you have these numbers now. You have all these number of traffic accidents per day, which your transportation department will collect. And from there, you want to know, you want to kind of predict something for the future, and for that, you approximate by Poisson, and then there's only one free parameter, which is lambda. And what is the best estimate for lambda? And that's simply the sample mean. And this, you know that for a Poisson distribution with parameter lambda, the sample mean, the expectation is lambda. Okay, so this is a natural quantity. Okay, and this was kind of similar for the Bernoulli P, because you know that the expectation of a Bernoulli P random variable is precisely P. P times 1 plus 1 minus P. So that is why, again, the maximum likelihood estimator was precisely the same. Yeah. Okay, so far we have done examples where there was, yes, question?
Sir, earlier also we had done the same example in which we had just said that if the average number of traffic accidents, say it was 3, then we know that the expectation of x is 3 and x is a Poisson random variable, so we can say that lambda is 3. And
right.
over here,
but here this is more quantitative. We are giving a reason. Now, I mean, so the point of view is different there. Here the point of view is to determine what quantity should you measure from the data. So you have this data x1 up to xn, and you know from some heuristic reason that it's best to take the Poisson distribution. Then what should you measure from the data to get out lambda, and what is the best quantity that you should measure? That is the sample mean that we have sort of proved. Okay. There
yes.
it was given that your Poisson, and then you are asked to calculate the probability that there's no accident in a day or something. So the point of view is different.
Yes, sir.
Okay. So now let us do another example where there are more than one parameters, and the natural example is so n independent normal trials with mean mu and variance sigma square, and x1 up to xn, and we want to find the maximum likelihood estimators for the pair mu and sigma. Okay, so we want to do both simultaneously. All right, so let's recall the likelihood function. So the likelihood function is f of x1 up to xn, given now mu and theta, sigma, And again, this is going to be a product. I mean, it will be more compact to write it using product notation. So product I equal to 1 to n. I have sigma 1 by sigma square root of 2 pi. And then I have e to the minus xi minus mu whole squared by 2 sigma squared. Right? This is now the PDF, probability density function. Okay. Okay. So now I need some space. So I'll expand all of this out. So I have 1 by sigma to the n, 2 pi to the n by 2, right? And instead of writing e to the minus, because I have a fairly large expression, I'll write x of minus, sigma I equal to 1 to n. Product in the exponent becomes a summation xi minus mu whole squared divided by 2 sigma squared. Okay, 2 sigma squared is common, so I can use some of that. Okay. So now I take log f. So log of f, again same, I'll just write log f for short. This is what? So I have minus n log sigma minus n by 2 log 2 pi. I mean, I could forget this because it doesn't depend either on sigma or mu. Minus 1 by 2 sigma squared. Oops. Log of the exponent is the same thing. So this is sum I equal to 1 to n xi minus mu whole squared. Okay. By the way, please stop me if there are any doubts in the computation. Okay, so now these are two parameters. There are two parameters, mu and sigma. And so if you recall from your UM102, you have to set the derivative, partial derivatives of log f with respect to both mu and sigma equal to 0. So d by d mu of log f is what? Well, this does. There's nothing here, nothing here. The only thing is here, and when you take the derivative of any one of these terms, you will get twice xi minus mu. So the one that 2 will cancel. So I'll have 1 by sigma squared, sigma I equal to 1 to n xi minus mu. Right? And which is equal to x1 plus up to xn minus n mu divided by sigma squared. And now if I set this equal to 0, the value at which the value of mu for which this is 0 is again the sample mean. Okay, so no surprise, right? So you want to set this equal to 0, and so you get this again. Let me stress that. Right? Okay, but what about sigma? And here there's something slightly surprising. So what would you guess would be a maximum likelihood estimator for sigma?
The sample variance.
Yes, that would be the natural guess. Right? I mean, what else? I mean, that's staring you at the face. But let's see what happens. So let's take the partial derivative with respect to sigma of log f. So what happens? So the first term will give you a minus n by sigma. The second term is a constant, goes away. Here I'll get something from sigma squared. So So I will get, because of the minus and the 2 there, I'll get 1 by sigma cubed, sigma I equal to 1 to n xi minus mu square. So this should be mu hat. So the value of sigma for which this is 0, and now I use mu hat here. Is what? So 1 sigma cancels out. I mean, sigma is not 0, so cancels it out. So you get 1 by this term is equal to this term. Sigma 1 sigma cancels out. So you take the sigma on this side. Okay, so maybe I should. So n is equal to 1 by sigma squared. Sigma equal to 1 to n xi minus mu squared. And so sigma equals square root of orbital square 1 by n summation I equal to 1 to n xi minus mu. Okay, so here I should. Okay, sigma hat. So you see the problem. So this is not the sample variance, sample standard deviation. So warning, this is not the sample standard deviation. Why? Anybody?
So because of n.
Because mark it in red. Not n minus 1. Okay. So it's slightly off, and this causes some confusion, but this is important. Of course, for large n, these two n and n minus 1 are close enough, but not. Yeah, so there is some slight issue, and this is related to something called the Bessel correction. So if I have time, I will come to that. Okay, so now I leave it for you, leave it as an exercise for you to find the maximum likelihood estimator for lambda in exponential lambda samples. Okay, so you have a bunch x1 up to xn. X1 up to. Okay, so I ask you to find the maximum likelihood estimator, and here it's not exactly the same as before, because why? Well, because what is the mean of an exponential lambda random variable? What's
1 by lambda.
1 by lambda. It's not lambda. So anyway, I leave you to do the calculation. It's not difficult. Okay. So last time I think Anirudh asked if every time we seem to get the sample mean as the maximum likelihood estimator for our parameters. So let's do an example where this is not the case. So n independent. Oh, sorry, I should continue to use my terminology from before. What is that? Yeah. So fourth example. If you want, this is the fourth example, and fifth example. N independent. Uniform 0 theta samples Okay, so one parameter I'm keeping fixed. I mean, this is not so restrictive because what many times the things that you're measuring are positive. So the lower limit is free and the upper limit is theta. So you don't know theta, find the maximum likelihood estimator for theta. Okay, so likelihood function again is f x1 up to xn given theta is what? So here it's tricky now because the uniform is a compact distribution. You have to be a little careful. So what is the density for uniform 0 theta variable? Yes, so on.
1 by theta.
1 by theta. So you have 1 by theta to the n, but provided that 0 is less than xi is less than theta for all I, and is 0 otherwise. Right? So each of the samples has to be within 0 theta. Right? So you want to maximize this. Now, okay, so we don't need to take the log function. So we want to maximize one by theta to the n. Okay, and you want by changing theta. So what value of theta should you choose? What is your guess?
The minimum possible value of theta that we could choose.
That's right. But what is the minimum possible value of theta?
It has to be equal to theta cannot be less than any data point. So we have to choose the maximum of x1 to xn.
Wonderful. Yes, that's exactly right. So I wanted you to fall into the trap and say theta equal to 0. But of course that doesn't make sense. Right? So you want to maximize this. So theta should be the smallest possible. But by this clause, all your samples are taken from this random variable, right? So from the uniform random variable. So if they fell outside this 0 theta, then this makes no sense. I mean, you shouldn't get the probability of getting any value outside your interval is 0. Well, okay, any value is 0, but any range outside the interval is also 0. So, but since all the samples must, let's say the sample must belong to 0 theta, we have rather here maximize the maximum at theta hat, which is the max of x1. Okay. So Anirudh, I hope you're happy. This is an example of an estimator which is not the sample mean. It's in fact the maximum. Okay. Any questions about any of this? So I'm going to move on to a new topic. So if you have any questions.
Sir, are we being loose on inequalities over here? Like it can be 0 open to theta closed.
Yeah, sure. Yeah, we are being loose. Yes. Because these are continuous distributions.
Okay, sir.
I mean, this maximum will be the closed, but yeah. Okay.
Sir,
Yes.
if we let's say we take many such we generate uniform random we generate x1 to xn from a 0 to theta, where theta is not known to the theta is not known to the person, and then obviously the maximum likelihood estimate will always be is equal to the maximum of these guys, but it will be practically even if we generate a large number of x1 to xn, it will still be slightly smaller than the true value.
Yes. No,
So
that is yes.
so can we say that the expected value will tend to the expected value as n tends to infinity of theta will tend to maximum of x1 to xn?
I don't know what you mean by expected value. I mean, these are data points, right? So as n gets larger and so first for the first few values, this theta hat will maybe increase fairly regularly, but then after a point it will increase very rarely, right? This is the best possible thing that you can do. It is correct that from a uniform 0 theta sample, you are never going to get theta. So, but we are now in talking statistics, and we want the best possible thing that does the job for us, and the max is the best thing. You're right. So this will never be equal to theta. Yes, that is correct. But this is the best we can do under the circumstances.
Yeah, yes, sir. Actually, I found a way to make make the question slightly more rigorous.
Huh.
Let theta itself be 0 to 100 or whatever. And let theta itself be a uniform random variable, or some sort of random variable. It could be any random variable. Theta come from a distribution, so person one takes theta from this distribution and plugs in uniform 0 to theta and gives the x1 to xn to the second person. How can we say that from x1 to xn, let's say we are given m samples of x1 to m sets of x1 to xn, then
Sure.
can we say anything about the expectation of theta from the unknown distribution that it's coming from?
Yes, I mean, certainly you can do that, but that is a different question. See, this is somehow the problem. I mean, this is the difference between a real world problem and a mathematical problem. I mean, so in some application, people really want to know this theta as best as possible, and this is the only thing that makes sense. I mean, you're thinking of compound random variables where the parameters themselves are random, but that's another question, right? I mean, so I don't know if you're measuring lengths of leaves or something in a tree. I mean, you have that tree and you have those leaves. I mean, you can't, you don't have anything else. So, so this is the issue that one has to make do with whatever one has. You can change the question, of course. And then you can solve something, but in many cases that will not pertain to reality. This is the issue. Okay.
Yes, sir. Actually, I did get why this is the best practical estimate for a working solution. For if we need some theta to work with, then obviously this is the best from one sample. But what if we had more than one sample? Should we merge them and then take the equivalent sample, or should we do something else?
No, that's okay. So such questions we will come to later on. Yes. So that is certainly a fair question. Right now we are assuming that this is the only data that we can collect, and then so x1 up to xn, maybe n is large, but that you can do it in one shot and that's it. So given that, then this is all we can do. So I mean, this happens in many situations, right? I mean, you can think of an election has happened and you want to know what the result is. I mean, we can't keep redoing the election just because we want better data. It makes no sense. So it's like that. We have to do the best, and questions like what you asked are when we come to hypothesis testing, we will try to answer such questions. Okay.
Okay, sir.
Okay. So now I'm going to move on to another topic. So before I do so, let us refresh. Let me summarize. So far, what we have seen are so-called point estimates. i.e. A single value, and maybe this is what Aditya is also kind of uncomfortable with, and I understand that completely. For the estimate. So, but I mean, we expect. I mean, nobody is believing that the true value will be exactly the same as the estimate that we obtained. Right? We expect the true value to be close to this estimate. But not equal. I mean, I think it would be perverse to assume that you will get exactly the same value, right? And a natural question is how close? I mean, how close is close enough? I mean, if I get some value as 3.5, I mean, what is good enough? Is 3.6 close, or is 3.51 close, or 3.501 close? It's like that. So you want to get some idea of scale, and so it is in many contexts. It is more useful to specify an interval where we are reasonably sure the true value lies. Rather than saying, okay, this is the value, I say, okay, the value lies between this and this. And so let us quantify that. Okay, so in many applications we will deal with IID normals. So let's take that thing. So these are called intervals. Okay. So from point estimates we are now moving to interval estimates. So suppose x1 up to xn are IID normals with mean mu and variance sigma square. Then x bar is the maximum likelihood estimator for mu. And so we have already know that x bar has distribution, again normal with mean mu and variance sigma squared by n, right? The sample mean. Okay. So what this implies, again, we have seen this before, x bar minus mu by sigma by root n, which is square root of n, x bar minus mu by sigma, square root of n is outside, is the standard normal, right? So now I'm going to appeal to some fact about the standard normal, which I will unfortunately have to ask you to memorize. So 95% is somehow the gold, not the gold standard, maybe the silver standard. So for Z a standard normal, the probability that mod Z is less than 1.96 is approximately 0.95. And I am going to have to ask you to remember this figure 1.96, and if it helps you, this is 1.4 square. 196 is 14 square. And this is something we can read off from the table. So in the end of your book, in the appendix, there's the table of values for the standard normal, and so we want so what is this? You remember the bell curve. So this is standard normal. So this is minus 1.96 and plus 1.96. And if your value lies here, then you are 95. I mean, this has area 95%. Okay. So how do you see that? So how do you read this table? So you're in the along rows, you have the larger significant numbers, and the second decimal places are in the columns. So if you want 1.96, it is this value, and so the probability that Z is between plus or minus 1.96 is you take twice this value and subtract 1, and you will get 0.95. Okay. So that's how this number is chosen. This is approximate, but we will often write equal. Okay, so this I'm going to ask you to memorize, unfortunately. So this 95% occurs at 1 point, within range 1 point. Okay, so therefore this guy is a standard normal. So let's write this. The probability that minus 1.96 is less than square root of n, x bar minus mu by sigma is less than 1.96 is approximately, but we'll write equal to 0.95. That's good enough for our purposes. Okay, so now let's rewrite this. So I'll manipulate these inequalities. So this is probability of minus 1.96 sigma by root n less than x bar minus mu less than 1.96 sigma by root n 0.95. And now I'll switch the sign. I'll write so actually I can replace this by mu minus x bar, because that will switch the sign and change the inequality if I multiply by minus 1, but these two are the same up to sign. So I'll get the same thing. And so now what's the final thing? I'll add x bar to all inequalities. So let me give myself some room. So probability that x bar minus 1.96 sigma by root n is less than mu is less than x bar plus 1.96 sigma by root n is 0.95. So what's the story? What's the moral? So thus the mean will lie within 1.96 sigma by root n of the sample mean (95% of the time). Okay. So not only do I have an estimator for the mean, knowing sigma, I can say something about where the mean should lie. Okay, and you can see it depends on n, and the larger n gets, the closer, I mean, the smaller these numbers get, and the narrower your interval becomes. Okay.
So,
yes.
but we don't know sigma, right? We can only estimate sigma from the point estimator.
Right.
What
So
sigma?
yes, we will discuss all those things. So for now, I'm just saying that if your random variable comes from normal with mean, mu, and variance sigma. So here I'm not. I'm really using the distribution. I'm assuming mu and sigma are known. Okay. But I'm going to come to the point that you're making. So let me define this. So let small x1 up to small xn be a data set from an n mu sigma squared distribution. Then we say that with 95% confidence, x bar minus 1.96 sigma by root n is less than mu is less than x bar plus 1.96. Okay. So if you want to underline this also. And the interval x bar minus 1.9 minus 1.96 sigma by root n to x bar plus 1.96 sigma by root n is a, you might have heard this phrase, 95% confidence interval estimate for me. So here, as I think Soham pointed out, the variance is known. So suppose you know the variance, then and you have this data set, then you take the sample mean of the data set and you add and subtract 1.96 sigma by root n to get a confidence interval estimate for. Is that clear? So there is a caveat here, so I should warn. It should be. There is a. One has to be careful here, and this is a cause of a lot of confusion, especially in the popular media. So what we are not claiming, so now we have to be a little careful. So we are not claiming that the probability that mu belongs to x bar minus 1.96 sigma by root n to x bar plus 1.96 sigma by root n is 0.95. This is not what we are claiming, because we don't have an underlying, since, I mean, when you claim that probability of mu is something, you need to have some random variable underlying mu. I mean, we need to say, we need to have some probability model, some for mu. We want to say that mu comes from some distribution, right? That's like Aditya was proposing earlier. But we don't have that. Mu is a number, right? So since there are no random variables here, we have, this is purely data. Right? That's why I use small x, small x1 up to small xn and small x bar. This is so you have a bunch of numbers which are x1 up to xn. From there you take this x bar, and you construct this interval. This cannot be a probability, right? What we are saying, and again this is similar to what Aditya was saying, that this technique that we have used, this methodology, results in mu being in this interval 95% of the time. Okay. I mean, if you are a frequentist by inclination, maybe you don't see the difference. But this is like what Aditya was saying earlier about constructing these samples many times. So if you take x1 to xn once, and then you take it again, and then you take another realization m times, and then 95% of the time, or 0.95 m times, mu will belong to this. So that is why we use the term confidence interval. We are not ascribing probabilities here. We are just ascribing some numerical measure of our belief. And that's why this term confidence interval is used. Okay. So let me give one example and we'll stop. But if there are any questions, please ask. This is a subtle point. Okay. You might say that, we have already said that we are talking about random, I mean, we are taking samples from a normal distribution, so there is a normal random variable. But the problem is that there is no random variable for mu. Okay. So this is a subtle point. So if you need clarification, please ask.
So,
Yes.
we started from the probability of a random variable being in some range, and
Yes.
that was 0.95. That is the probability that x minus mu upon sigma upon root n lies in this interval. The probability of that is 0.95. So why is the interpretation that the mean lies in between with a probability 0.95 not correct?
So that's what I was saying. So here, this construction was purely, so I use capital letters here deliberately. So here I am assuming that I am taking samples from a true mu sigma squared. I mean, this is a theoretical construction, and I am saying that we know from the error function that the probability of the average of these random variables will satisfy this, which is x bar, will satisfy this equality, right? But now we are talking about samples from some data set, and as you rightly pointed out, there is this underlying distribution, but we cannot say that mu belongs to this with some probability. I mean, this point of view has shifted. because now mu is the unknown object. I mean, it's known, but I mean, not that it's known. I mean, we want to predict mu. Okay, so we don't know mu, and we are trying to get some information about mu from the data. But therefore, I mean, all you can do is, take this interval and say that mu will lie here with 95% chance. Okay, so since you are performing this this realization only once, x1 to xn, you don't have any probabilities. You cannot, you don't have a model for mu, as I was saying. Okay, so
Yes, sir.
so the frequentist interpretation is what's coming in here. So 95% of the time mu will belong here. So in that sense, it is a probability, but it's not a probability the way we have been talking about probability, because we do not have any random variables for mu. Okay, we do not have any model. We are not saying that mu is distributed with maybe uniform distribution or something in some range. We are trying to get out a number, and we are saying that that number lies in this interval with this confidence estimate. Okay.
Yes, sir.
Okay. So let me finish with an example. So in an experimental measurement, yes.
So, sir, so in this in this question, basically, what we have done is the probability is not 0.95. The probability just does not exist. Is that what you're trying to say?
Exactly. There is no probability. There are no random variables. So what we are saying is we are, as I said, ascribing some numerical value to our belief that mu lies here. Okay. That's sort of the Bayesian kind of point of view. Okay.
Okay, so it is a
So
specific iteration of the random interval.
yes, iteration.
I mean, after many times you can do the experiment, right? So in this
Yeah, you
specific,
can't. No, but you can't. You can only do it. I mean, that's what you have, right? You have x1 up to xn and nothing else. And you know sigma from whatever background data.
okay,
Right?
okay,
So
okay.
that's so our limitations force us to say such things. That's the point. I wanted to finish this example. Okay, I'll finish it quickly. Yeah, sorry for going over time, but there were a lot of questions. So in an experimental measurement, let's say the noise is distributed is normally distributed with mean 0 and variance 4. Okay, this is just the noise, not the actual data. The quantity is measured 9 times resulting in the values, these 9 values, which I'm going to list now: 5, 8.5, 12, 15, 7, 9, 7.5, 6.5, and 10.5. Okay, these 9 values. So you want to construct a 95% confidence interval estimate for the value, for the true value. Okay, so we take, so we assume that the measured value equals true value plus noise. So therefore, this true value is has mean whatever and variance 4. Right? So that's what we. So thus x bar, I claim if you sum all of these things, you'll get 81 divided by 9, and that's okay. Which is a maximum likelihood estimate for mu. So, and moreover, sigma 1.96 sigma by root n is 1.96 times, this is, sorry, variance is 4, which is sigma squared, so this is square root of 4 divided by square root of 9. So this is 2 times 1.96 by 3, which is whatever it is, and the interval is 9 minus this value to 9 plus this value, which is approximately 7.69 to 10.4. Okay, yeah, sorry for going over time. Let me stop here. Oops.
Sir, but the mean was the measured value. I mean, the values were the true value plus the error, right? So how did we say that the variance is variance of the measured value is 4?
Because I'm just shifting the variance. I mean, if z is a normal variable, random variable, then z plus a is also a normal variable with this, with the mean shifted and variance the same.
Yes, sir, got it.
Okay, so let me stop recording. Sorry for going over time.